let's now talk about regression classification trees. The basic idea in both of those models, and let's focus on the regression trees first, is to have a very simple model where I effectively do a prediction which is just a constant or an intercept. So kind of, if you look at the linear regression problem before, where we had kind of any linear function, now just say my function is a constant. And it's kind of intuitively clear if I have some data points here, and if I want to fit the kind of best constant, this would just be the mean of this function. Kind of, it also follows from the kind of general solution which we calculated last week for linear regression. We can just specialize it to a case where we just have a constant. We can actually see that the result is that the optimal constant is just the mean. If you can't remember, we can also quickly calculate it. So if you wanted to, for example, minimize the least squares here, we want to minimize the sum of squares, we would take something like y minus, now we have this intercept a times just a vector just of 1. So this one vector is just 1, 1, all ones, which is exactly the first row of our, the first column of our model matrix. Now we kind of transpose it, and we take y minus a, oh sorry, it's a scalar here, 1 vector, and now we just want to basically differentiate with respect to a to find the best intercept, and we can do that exactly as before, and then we set it equal to 0. So if we do that, we will get something like minus 2 times, and then we have 1 transpose times y vector, and then minus 2, and here I have a times 1 transpose 1 basically. So if I have that, I can actually see that now if I set this equal to 0 and I solve it for a, I will get something like a is equal to, and now I have 1 transpose y over 1 transpose 1. But if this one has n elements, then 1 transpose 1 is just 1 plus 1 plus 1 plus 1 n times, so it will just give me n, and this 1 transpose times y will just be the sum over yi. So this is exactly the mean. So we can see that, just to provide some little details, we can see that if we fit a constant value, it's just the mean. And this is, you should basically know it from the linear regression lecture last week, but it's a very specific case, so it's good to remind ourselves about that. So what would happen if you, for example, take some data, again there's some kind of toy data, simulated data here. So if I fit the mean, I will get this dashed line. So the mean would just be this line here, which is roughly at, I don't know, like 3.7 or something like this. But we can see in this type of data, there actually seems to be regions of kind of changes in the data there, where the data seems to be slightly higher on the left, a bit lower in the middle, and again higher to the right. And I could ask, for example, could I maybe fit a mean to different regions of the data there? And there the question might be, how many regions of the data? But one thing I could say, for example, well, what if I would try to fit 2 different means here, and I would find where would be the best possible point to split the data to fit, say, a different mean on the left or to the right of this splitting. And it would be, for example, you can see by eye that if I kind of split the data here, and I would say fit a mean to the left, I will get something like this, and a mean to the right, I will get something like this, you see. So that would be a better fit to the data by eye, and you can actually see, if I would now calculate the, let me use a different color here. So if I would calculate the residuals squared to the orange line, where I kind of look at the distance here between any of the points and I square it to the orange line, then this will be larger than this one here, if I calculate it with regard to the blue line here, which would be the residual squared when I have the blue line fitted. So this is kind of seen by eye, but actually if you would do the math, you would see that the blue line would be a better fit. But who says that maybe I have to kind of split it only once? I could split it twice, for example, and if I would try to split it twice, I would get yet a different one. Probably I would find that the best point to split the data further might be somewhere around here, and then I would get a different fit, which could be this green line here. I would get the same thing here, but here we get something lower, and here we get something higher again, just by looking by the eye here. So my fit would be something like the green line, if I would now do 2 splits, for example. And the basic idea of regression trees is exactly that. Let me kind of look and try to fit a constant function. Let me try to split the data and see where's the best possible splitting point to get a lower residual sum of squares if I fit a constant mean which is different on both sides of the splitting. And I can then keep on doing. I look for the best split first, then given this first split I can look for the second split, and so on. It's again greedy, like we saw greedy algorithms when we talked about subset selection. I will kind of keep the choice. I found the first split was here. This was the kind of best line to split the data in 2 halves. I will keep it, and now I look for different splitting points. Could be on the left or on the right, and I will keep on splitting the data and find kind of constant fits to the data. You might ask yourself, well, how am I going to compute this? There are kind of infinitely many splitting points. How am I searching for all of them? But you already see that kind of determining the split kind of between 2 data points, it doesn't really change the mean. I mean, there are only so many different splits as there are data points here, basically, because there's no difference changing splits between a kind of empty space between some data points. It doesn't really matter. So there are only n possible points where I can split the data if there are n points in one dimension. So this is an example here. So here I plot again. This would be the kind of best piecewise constant function for 2 splits here. And now we see that while each kind of region, each interval has a constant fit, the total function here is a nonlinear function. So here I fitted a nonlinear function to the data by effectively just asking myself to fit piecewise constant functions to given intervals over the data. And this is the basic recipe behind regression trees, effectively just summarizing what I already said when talking through the picture earlier. I effectively go through the data. I will look for the best binary split amongst all predictors. In this case there was just one variable here, according to some loss function. In this case I looked at the residual sum of squares, and I will see how much goes it down if I have different splits here, as I explained in this picture. If I go from the yellow line to the blue line, the total residual sum of squares will get lower. And it can only be lower or equal than without the split, kind of by definition, as you can convince yourself. And then kind of given the previous split in a greediest manner, as I explained earlier, we kind of keep on splitting further in the same way as we did before. And kind of why is it called a regression tree? Because you can kind of phrase the whole thing in forms of a tree there. So the tree describes the structure on how I split the data. For example, here I first splitted my data by this point here. If x is less than 3.95. So this was the case here. If I jump back to the picture very quickly, so here was 3.95. If x is less than 3.95, I'm in this region here. And if I'm in this region, I kind of give back this value here. And this value is 4.5 4.59. So I'm kind of giving back, sorry, 4.59 if I'm to the left of this point. Now then, if I'm to the right of this point, I will do yet another split here at 6.95, and this is exactly what I'm seeing. Now I'm on the right of this point here. I'm to the right, and now I'm splitting at another point, which is this one here, which is exactly this 6.95. So now, if I'm below 3.95, I directly split out this value. If I'm to the right, I do a further split, and then if I'm to the left of this further split, I give a value which is roughly 2, and to the right I give something which is roughly 4, which is exactly what you see here. If I'm to the left of this, I will give this value which is roughly 2, and if I'm to the right of this, I will give this value which is roughly 4, approximately. And now you can see this nonlinear function, the green line, is exactly defined by this tree here. This defines exactly this nonlinear function. It has the splitting points here, the one at 3.95, the other one at 6.95, and all it says, if I'm to the left of this, I split out this value, 4.5. If I'm to the right of it, if I'm to the right of this, I will do a further split here, and if I'm to the left of this point, but to the right of this point, I will put out 2 here, and otherwise, if I'm to the right of this, I will give a value of 4 here. So this is exactly this function here. It's a nonlinear piecewise constant function which is defined by this tree. I hope this makes sense. And this is why it's called a regression tree, or we'll later see classification trees. The tree are just the rules of how I split the data into piecewise constant functions there. And what's interesting, if you look at it, so this was just a 1D example, I had just one predictor x, but I can do the same with 2 predictors. I could have x1 and x2, and now the procedure is exactly the same, but I can be splitting. I can ask what is the best split in this kind of direction, but I could also ask what is the best split in the other direction. I can compare them for all directions, or all predictor variables, and then I can choose the best one. What is the best split amongst all possible best splits for all predictors? And this is the one I choose. What's quite important is that if I think about the regions in space which I can get, so here I can see I can get kind of those intervals for my constant intervals. Obviously, these are kind of partitions of the data of the predictor space. In this case, it's a 1D space. I'm kind of partitioning it in intervals. But if I have 2 predictor variables, I could ask myself, how can I now partition this 2D predictor space between x1 and x2? And what's important is that I can't get things like this one here. If I follow this greedy rule, I mean, if I do any partitioning, I could get something like this. But if I use this greedy procedure, I can't get something like this, because I'm always splitting effectively by saying, what if something is below in this direction, and then it's below above in this direction, then it's below above in this direction, then it's below above in that direction. I will never get a kind of funny shape like this, as you can easily convince yourself if you will do this slicing in this form. But this is not to say that the model could not represent something like this. For example, if I would split the data, I couldn't get this funny form, neither I could get this corner. But if I had split the data like this, and say like this would be a totally kind of fine splitting of the data, which I could have gotten very easily, or even I mean, it would not even have to kind of go through here like this. Sorry, now I deleted everything, but it could have been even easier. I could have just drawn those two here. Now this would have already been possible as a possible splitting here. It's just now I can say it's to the left of this or to the right of this, and if it's in the middle, I will just split with regard to this and that. So that's possible. The other one was not possible, but I can see already that kind of this region I had before, if I just introduce another line here, I could get exactly this red region with one constant if I were to choose the same constant for all those three intervals. So I can see, even though I can't do these funny shapes, I could still approximate a function over these funny shapes by effectively looking at something more detailed and then choosing the same values for those three regions here. I can effectively get the same as choosing a constant over this more weirdly shaped region there. So I can't do all possible shapes, but I can still approximate it. And this is why this greedy approximation is a good approximation, even though I can only split greedy, but I can eventually approximate something even if it's not directly compatible with this splitting here. So let's just have a look at this specific example, the one we have seen here. So this is kind of obviously a 2D predictor space. Those are possible splittings here in the space of x1 and x2, and obviously the value of this function is now in 3D. The output, the response variable, is some three-dimensional functions, and I can look here how that looks like. For example, this is just one example how this regression tree looks like. So here's this x1 variable, and now the first thing is I'm looking for x1. If x1 is less than t1, this would be this line here. So here's t1. Now I'm splitting, or I mean not just this line, it's this whole plane here effectively. This is this plane where I'm splitting in. If it's to the left here, to the left would be this region. If it's smaller than t1, then I will go down this route of the tree, and then I will compare again, but now compare the other variable x2 here. x2 is less than t2. So here, this would be t2 here, and now I'm basically saying if it's less than t2, then I will get this region R1, which would be exactly here. This region here would be R1, but if it's above t2, I will get R2, which would be that region. Now I've covered everything to the left of t1 here. Now I look further, what happens if x1 is bigger than t1? Then I go down this route in the tree, and then it corresponds to everything which is here in this direction. Now I'm splitting again x1 at a different point, t3. This would be this point here. This is exactly t3. Now, if I'm to the left of this, I will get the region R1, which is just this region, R3, which is this region here. Now, if I'm to the right of it, so I'm here, so I will go down this route, then I will do one more splitting, but now in the variable x2, which will be x2, and now I'm looking at this direction here. Basically I'm splitting at this value in x2, which is the value t4, and if I'm smaller than t4, I will get this region R4, and if I'm bigger, I will get this region R5. So this is just labeling all those regions here as they emerge from this splitting here, and it should hopefully be exactly the same as in this figure here. R1, R2, R3, R4, R5 are exactly those regions which come out of this tree here, and this is kind of the 3D picture of the function which we talked through. I mean, have a look, go through it in detail, but this is the way it works. And how does the tree come up? Obviously now just showing you that this tree corresponds to this function, but how did we come up in the first place? There was some cloud of data, and we looked at the direction x1 and the direction x2, and we asked what are all the possible splitting points? We already know there are only as many as there are data points effectively, so I go through all the splitting points, compare the mean of left and right, and look what will be the kind of smallest reduction in least squares error of the total function, and I do the same for the direction x2, and I compare them. In this case, the reduction in the variable x1 was the smallest exactly when I split in at around t1. So this was my first split. After I've done the first split, I can then go for each side and see how do I split further, and so on and so forth, and I kind of keep on constructing those regression trees. So this is just the basic idea behind regression trees, and I hope you can see that the principle is actually quite simple here. It's only piecewise linear functions, but again, I can see how I can approximate any nonlinear function. And one thing which I can also see here is that the more splits I have, the more nonlinear the function becomes. For example, here the least flexible function would just be the straight line in this case, the orange line. This is the least flexible function. Now, the more flexible function would be the one with one split, which would be something like this. It's something which moves, but at least it's only going down. And then the more complex function would be the green one, which goes kind of down and then up again. And I could also go further. I could do 4 splits, 5 splits. I can do up to n splits if there are n data points, basically. But kind of the basic idea here being that kind of the more splits I do, the more nonlinear the model becomes. And it's also interesting to see that the number of splits is directly related to the number of leaves here of the tree. Well, this tree is upside down, but you can think of it, this would be the stem of the tree, those would be the leaves, they are called leaves, and the internal ones are called nodes, basically. So this tree has kind of 2 nodes, it has 3 leaves here, but obviously the number of splits and the number of leaves are directly related. I can see here also this one has kind of 1, 2, 3, 4 splits, and it has 5 leaves. So there will always 1 more leaves than there are splits, basically. But so splits or leaves, I can effectively treat them equivalently, apart from this difference of 1. They control the flexibility of the model, and you probably already guessed, how do I choose the number of leaves? Using cross-validation. I can basically start with trees of like 1 leaf, 2 leaves, 3 leaves, and so on. I can kind of increase it, and again do my cross-validation, look at the test error and see when is the test error minimal. This would be, say, the best number of splits or leaves. Could be 3 splits or 4 leaves, for example, which would be the best outcome for this case here. If I look at the data, 2 splits or 3 leaves would be the best for this data, just by looking at the eye of it, because I know what the real data was. I simulated it. Anything else I would be fitting to the noise, and then in this case the test error would be going up again. Sorry, it would be 2 or 3. So 2 splits or 3 leaves would be the best for this other example here. And that's exactly how I choose the type of tree I'm working with using cross-validation. And then you can basically do kind of everything we talked about last week on choosing which is the best model to work with. Now, interestingly, besides kind of those regression trees, I can also do the same with any other response variable. Rather than saying, for example, in this region here, rather than giving a value, an output of a continuous variable here, I always give the same value for this region here. Say this would be, in this case, R1 would be this value. I'm not sure exactly what it is, but could be whatever, 3 or something like this. This would be 2, and it's a height here. Instead of giving out a height, I could also just give out a class label. In this region is cancer, and this region is no cancer, and this region is spam, and this region is no spam. So the basic idea works exactly the same. Obviously now, if I have these class variables, I don't talk anymore about least squares, and there are different loss functions now, and those loss functions are sometimes also called cross entropy or Gini index. But this is something you do not have to know in detail. You just have to know that if you go to Python, you want to compute classification trees rather than regression trees, that the idea of splitting the data into partitions is the same, but rather than spitting out one continuous value for each region, I will give you one class label for each region. And the loss function now is not anymore least squares or the residual sum of squares, which I want to minimize, so that's least squares, but it's a different loss function, is something called cross entropy or Gini index. A kind of exactly, I mean, feel free to go actually into the documentation, have a look what it exactly is, but kind of for the nature of this code, we don't have to know exactly what it is, but again, by minimizing it, we are kind of making our predictions more accurate. But exactly as we've seen with logistic regression, the loss function is not exactly equal to misclassification rate. It's something else, and I mentioned already that in logistic regression, it's actually quite closely related also to this cross entropy. If you actually looked what's the loss function, which there we derived using maximum likelihood estimation, what it actually means. But those are just some side remarks. The important thing is that we can easily extend our framework of regression trees easily to output variables which are not continuous but are class labels, and all we do, instead of fitting a constant continuous value, we now can just fit a constant class label there. And this was really all I wanted to say about kind of regression trees and classification trees. We kept it quite brief for classification trees because kind of once you understood regression trees, it's really the same principle, only that now the output variable would be a label rather than a continuous variable. One interesting remark though is that I mentioned it here at the beginning, those things are quite good. I can easily deal very easy as well with any types of variables, not just in the response variable when I go, say, from regression to classification trees, but even in the input variables. Kind of now we assumed this is like those dimensions x1 and x2, they're just continuous variables, but x1 and x2 could also be of different nature. For example, x2 could be, rather than a continuous variable, could be a discrete variable, which could be, I don't know, colors of cars or something like this. And then I could say, well, if the car is green, I will go down this wood of the tree. If it's not green, I will go down that wood of the tree, and so on. So I can deal also with other input variables. And most importantly, I can also easily deal with missing values. Missing value is just like a different split in the tree. I can say, here's a variable x1. If x1 is NA, basically if NA, I will go down this wood in the tree, and if it's not NA, I will go down this wood in the tree. So I can very easily introduce kind of different categorical variables and also NA variables inside of the predictor space. So those trees are very powerful. I can easily deal with variables which are not necessarily continuous for the predictors, but also discrete variables, and I can directly deal with NAs without having to worry about them. They're just treated as a special label, and the tree can kind of decide to choose a special branch of the tree for the special value, which is just missing value. And also I can very easily deal with different outputs. So regression classification can be dealt with the same type of model. It's just a different loss function here. That is all what changes, but the kind of partitioning of the space works exactly the same. And here you see already that those trees are quite powerful. And now we will actually see that while the trees are powerful, they are not the best in terms of kind of performance of the model. We can actually squeeze out a lot more performance by some other techniques, which we will discuss in the following when we talk about random forest and boosting. What is important though to say is that trees are still very important in practice, because trees are very nice that they are interpretable. You can easily look at the model and say, for example, why did I get this output? Why did my model say we got the value R1 as a result? And the nice thing as well, because this predictor was less than T1 and this predictor was less than T2, this is what I got the value R1 out. So there's a very easy reasoning behind it, and that's why they're still used. For example, in insurance companies, if someone gets kind of gets a credit line refused, they might go to court and say, well, why did I get it refused? Am I being kind of wrongly treated? Is it because of my ethnicity or something like this? And then the kind of insurance company can go back and say, no, we use this tree here, and we can actually say it's because your age was below 20 and your income below this, and that's why we didn't do it. Nothing else, basically. So it's very nice and interpretable, which is kind of different to deep learning models, or even those ensemble models which we talk about next. They are much more difficult to kind of understand what the models can do. So trees are still very important in the sense that they are simple, easy to interpret. The performance, the accuracy might not be as good as some of the models we will be talking about next, but this the possibility of being able to interpret the results might still outweigh a kind of potential reduction in accuracy. So let's move on and now talk about boosting, which is the technique we use for the more complex models.